Welcome to ERC Tipsnology. In this video, we will be learning about the resistors in parallel. Two or more elements are connected to the same two nodes and have the same voltage across them, and this is what we call as parallel. So again, when two or more elements are connected to the same two nodes and they have the same voltage across them, then the resistors are connected in parallel. Now, each resistors are connected to the same nodes. It can be called node A and node B. And number two, they have the same voltage across them, which is equal to the voltage source Vs. For example, in this circuit, we have resistor R1 and resistor R2 connected in node A and node B. And so the same nodes A and B are connecting together the R1 and the R2. So this is parallel. They also have the same voltage across them. So whatever is the voltage value of Vs, that will be the voltage value of V1 and V2. Therefore, V1 is equal to V2 is equal to Vs. This is another example of how to connect the two resistors in parallel. So it's the same actually with the letter A, but there is a current symbol here, the IT coming from the positive of the voltage source, and the IT is also the one going back to the negative or the minus of the Vs. So this is the IT from positive or towards the minus. Now this is I1. The R1 will have one current here, I1, and R2 will have another current, I2. But you compared with the series, these currents, there are now three currents in our circuit. We have IT, we have one current going through R1 and another current going through R2. Now this is another example of resistors in parallel. We have four resistors in parallel. R1, R2, R3, and R4 are all connected in parallel. As you can see, the node A here and the other node here can also be called A because there's no resistor or any component between them. Also here, this is also called node A because there's no resistor connected over here. So it's the same point. You may make this short line or cancel the line on this part and put them together, the triple A letters here. Down at the bottom, you will see also node B. These are all called node B because there's no component between them. So we may opt or we may choose to put them together, the letter B. So we can say that the current I total coming from the Vs or going to Vs is equal to the I1 plus I2 plus I3 plus I4. This is called Kirchhoff's current law, which states that the sum of the currents into a junction will be equal to the sum of the currents out of the junction. Now, the junction that we are talking about is letter A here, and the other 2 points here is also considered as one junction A, and this is junction B. We also call it node A and node B. Now, to identify the parallel circuit, we will know it's parallel if there is more than one current path or more than one way for the current to pass. Or it will not just go to, it will not just have one way, but two ways or three or four or more than one between two components or between 2 points. The second one is that the voltage between those 2 points also appears across each of the branches, meaning that the voltages between or among the branches are all equal to the voltage Vs. So there's only one voltage in the parallel. Now here we have another example here where we have node A and node B, but this time the resistor is not over here. a parallel directly here, but on the at the bottom. But because it's still the same, whether it's at the bottom or at the top, they are still connected to node A and node B anyway. So it's still parallel. Here we have stretched the line here over here and make it looks a little different, but logically it's still the same. Physically they are not the same, but logically there's one current going into this node A, and it will split into two, and it will go to node B. Now the value of the current that will go here will not be equal unless the resistors are equal. If these two resistors are equal, the current that will be splitted or divided will be the same current. So if this is 10 amperes, one will be 5 amperes and the other one will also be 5. That is if they are the same. So there is more than one current way between the 2 points. So between point A and point B, there's two way, one going down and one going to the right. Here, one going down to point A and one going downwards towards the left and downwards towards the right. So there's more than one current way or current path. And the voltage between these 2 points, between A and B, if there's a voltage here, that will be the Vs, that's equal to the voltages between A and B. So VAB and Vs will be equal. So V1 and V2 will be equal. And the resistors are connected across the same points. This is another example. We have here node A, and this time there's three resistors, but this resistor, the second resistor on the right and the third resistor at the bottom are in series. Therefore, this is like a series parallel circuit because R2 in and R3 will be added first. So you have to get the sum of the R2 and R3 before you can get the parallel RT of the other resistor on the left and the total resistor or total resistance between R2 and R. But we will see that later when we discuss series parallel circuit. So actually, this is not only parallel. Again, this is two resistors in series, and after you calculate the sum, it will become one. Then it will be parallel to the first thread. But the point here is that the current coming from A going towards the node A is divided into two, one going this way and one. So there will be two currents produced by IT. Same with this one. This is still parallel because I total going to I is equal to I1 plus the I2. So on letter A or node A, the current will be divided. Same thing here. In node A, the current will be divided and it will go or come back together at node. So it's still parallel. And so with this circuit, the current will go to node A, go up, and then go down to node B. So this is still parallel circuit. So again, the Kirchhoff's current law or KCL is just adding the currents or the sum of currents going into a junction equals the sum of currents out of that junction, or the total current in equals the total current out. It's also said that KCL or Kirchhoff's current law is the algebraic sum of all currents entering and leaving a junction. It will be equal to zero. So the algebraic sum, or the sum of all currents in, is equal to the current out, or the sum of current out. So in this example, we have junction A or node A and junction B or node B, and we have I total going to junction A, and it will be divided into three currents. One current I1 will go up, I2 will go in the middle, and I3 will go down on the third resistor. But on the other end, we will have junction B, and all of the currents will become one again, and it will be equal to I total again, which will go back to the negative side of the voltage source. So we can say that the IT equals I1 plus I2 plus I3. Remember, in series before, the current is only one, but in parallel, the current is not only one. So the I total becomes three currents, I1, I2, and I3. And that is the rule for parallel. And we call this rule as Kirchhoff's current law, or KCL. So all currents going in, which is the IT, will be equal to all currents going out, which is I1, I2, and I3. Now, this is the general formula for Kirchhoff's current law. If you have one current input 2, input 3, and current input 4, and so on, up to, let's say, current input letter N. And we have current output 1, I out 2, I out 3, and I out 4, and so on up to I out M. So going to this node or junction, we can say that the sum of I in 1 up to I in N equals the sum of the I out 1 plus I out 2 up to I out M. So this is the general formula for Kirchhoff's current law. And they don't even need to be equal in terms of how many currents going in and how many currents going out. What we're talking about here is the sum of the current in and the sum of the current out will always be equal. Now, to have another example, we have here in 116, determine the current I2 through R2. So let's say that we have point A here and point B. So the current going towards or going in into A is 100 milliamperes, and the currents going out is I1, which is 30 milliamperes, and I2, which we don't know, and I3, which is 20 milliamperes. So to be able to calculate the I2, we will follow the Kirchhoff's current law. So by KCL, IT equals I1 plus I2 plus I3. And because we don't know I2, we can subtract the I1 and I3 from I total. So I total minus I1 minus I3 will be equal to I2. And that would give us 100 milliamperes minus 30 milliamperes minus 20 milliamperes will give us 50 milliamperes. Now, this is another example of the representation as a schematic diagram for the total parallel resistance. So as you can see on the left side, we have the voltage source, which has a corresponding I total, and the I total was divided into four. So we have I2, I3, I1, I2, I3, and up to I4 if there's four, but this is N. So we can take as many resistors as we want in parallel, but still it will be divided, or the I total will be divided depending on the number of resistors. So we can have a general formula of IT equals I1 plus I2 plus I3 plus and so on up to any number of resistors or IN. So the number of current paths also or ways, like here we have 1, 2, 3, 4. So the number of ways that the I total will be divided is 4 because we have 4 resistors in parallel. But it does not mean that the I1 will be equal to I2 equal to I3 or up to I4 or IN, because it all depends on the resistance values. If the resistors have high values, then the current that can flow through it will be affected, because as we have said, higher resistors have higher currents. So if all the resistors here have different values, of course the currents will also have different values, except if all of them are all having the same resistances. If all of them have the same resistances or the resistors are equal, then the currents will also be the same. But it will still be divided by the number of the resistors. So the total current entering the junction of the parallel branches, remember that a branch is like R1, this is one branch, R2, one branch, R3, up to Rn, will be divided into each of the branches. So the total resistance, as I have mentioned, is equal to I1 plus I2 plus I3 up to plus IN. Now, by using Ohm's law, we remember that I is equal to V over R. So if we want I total, that will be Vs over R total. If we want I1, that will be Vs over R1. Actually, this is equal to V1 over R1, but V1 is also Vs in parallel. I2 will be V2 over R2 or Vs over R2. because V2 is also Vs in parallel circuits. I3 is equal to V3 over R3, but it will also be Vs over R3, and so on. In will be equal to Vs over Rn. Now, remember that the formula for the R total is 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 up to 1 over Rn. But in general, the formula for R total is 1 over R1 plus 1 over R2 plus 1 over R3 and so on. This is the formula for the total resistance in parallel. Now, let's calculate the total parallel resistance between points A and B of the circuit in the figure below. So we have R1 100 ohms, R2 47 ohms, R3 22 ohms. We'll just take for now the total resistance. So again, the uh, the resistors are connected all on points A and B. So the formula is 1 over R1 plus 1 over R2 plus 1 over R3. So 1 over 100 plus 1 over 47 plus 1 over 22 ohms. Then it will give us 13.03 ohms. Now, if you compare the R total, it's 13 ohms more or less, but this the highest here is 100 ohms and the smallest is 22 ohms. Therefore, we can say that the total parallel resistance of 13 ohms is less than the 22 ohms, which is the lowest resistor in the circuit. So it means if we have parallel circuit, whatever is the smallest resistance, when you calculate for the R total, it will be expected that it will be smaller than the smallest resistance. That's why here, if you compare 13.03 is actually smaller than 22 ohms. Now, these are again, the connections of the parallel resistors. Don't be confused. This is just focus on the point A and B. As long as the two resistors are connected on the same points, the same 2 points, then it will be in parallel. So A is parallel, B is parallel because there's 2 points here. Actually, we can say three lines, one in and two out. Here, one in, two out. Here, two in, one out. So same. These are all pictures of parallel circuits so that when you encounter them again, you will not say it's a series, or you will be sure that it's really parallel. Now, if you only have two resistors in parallel, like in this diagram, the R1 and the R2 only, you can directly multiply the R1 and R2 and divide it with the sum. So R1, R2 divided by R1 plus R2. Just be careful with using the parentheses. So the total resistance of two resistors in parallel, this is a special formula only applicable to two resistors in parallel. It will be the product of the two resistors R1, R2 divided by the sum of the two resistors R1 plus R2. So the current divider formulas for two branches uh, can also be, you can also use this formula for the current this time. If we will be calculating current I1, that will be equal to R2 divided by R1 plus R2, or the sum of the resistors in parallel. This is only applicable for two branches. So if you only have two resistors, then you can divide the opposite resistance. For example, you want I1, do not put here R1, put here R2, and then get the sum of the two resistors and multiply it by I total. Now, if you want I2, take note, I did not put here R2. I put R1. So you write the opposite resistance. If you want I1, put R2. If you want if you want I2, put R1. So usually the error is like when you put I1 here, you put R1, then you will be wrong. When you put I2 here, you should not put here R2. Please remember that one. And again, this current calculation is only applicable for two resistors or two branches in parallel. Now, if you have more than two, like in this case, but the resistors have all the same value or equal values. As you can see, R1, R2, R3, R4, and R5 are all the same 2.2 kilo ohms. Then you can simply divide the R by the number of resistors. So any number of resistors having the same resistance, the R total is equal to the resistance given divided by the number of resistors. To make it clearer, let's look at this. So 2.2 kilo ohms divided by 5. 5 came from the number of resistors that we have. We have 5 resistors, so we divide it by 5 and we got 0.44 kilo ohms. Again, the total R or RT is smaller than the value of the resistor here. Now, the current divider general formula will be like this, and as you can see, we have I1, I2, I3 up to IN. N is representing any number of resistors in parallel. So, if we will be doing the general formula for R total, not two branches but more than two, this will be 1 over 1 over R1 plus 1 over R2 plus 1 over R3 plus and so on 1 over Rn. And then the R1, R2, R3 up to the Rn must be given so that we can calculate the R2. And then if you want to calculate the current I1, all you have to do is to put the answer RT divided by the R1. So this time I1 R1 here. So the R total, which we calculate from the first formula, divided by the given R1 multiplied by I total. The I total must also be given. So the I2 is RT over R2 multiplied by IT. I3 is equal to RT divided by R3 multiplied by IT. And in general, In is equal to RT over Rn multiplied by IT. So we can say Ix, X representing 1, 2, 3, and so on, is equal to RT over Rx multiplied by I total. Now, if we will make this in words, current Ix through any branch equals the total parallel resistance divided by the Rx or resistance Rx and then multiplied to the total current IT. So let's determine the current through each resistor in the circuit given below. So as you can see here, let's get a pen. We have to calculate or to determine. See. So we have to determine the current through each resistor in the circuit. So we have resistor R1 680 ohms, resistor R2 330 ohms, and R3 220 ohms. And then we also have the current going to this node equal to 10 amperes. So this will represent the IT. But we don't know I1, I2, and I3, but we know the R. So the first step is to calculate for the total resistance. So the total resistance can be taken from this formula. 1 over 1 over R1 plus 1 over R2 plus 1 over R3. And then substituting the values of the three resistors over here, 1 over 680 plus 1 over 330 plus 1 over 220, we will get an R total of 110.54 ohms. And that will be used in our formula for Ix. So the RT will be always 110.54. When we calculate for I1, the RT that we will be using here are all 110.54. And then the Rx over here will be equal to R1 if you want the calculation for I1, that's 680 ohms. And then we have R2 equal to 330 ohms, and we have the R3 equal to 220 ohms as given in the circuit. So if you multiply all of them by 10 amperes, then we will be getting 1.62 amperes for I1, which will be going this way. And then we will have 3.3497 amperes for I2, which will come from here to the resistor over here. And then we will also have I3, which is 5.02, will be coming from this way going to the right here. This will be the values of our currents, I1, I2, and I3. Now, in summary about the resistors in parallel, again, the resistors are connected across the same points. It has more than one way for current. The number of current ways or paths equals the number of resistors in parallel. The total parallel resistance is less than the lowest value resistor. The voltages across all branches are the same. The current sources add algebraically, and the Kirchhoff's current law, KCL, states that the sum of currents into a junction, which is the total current in, equals the sum of currents out of the junction, which is the total current out. And Kirchhoff's current law, KCL, states also that the algebraic sum of all currents at a junction is zero. We can say that a parallel circuit is a current divider because the total current entering the junction of a parallel branch or parallel branches will be divided into each of the branches. So if all of the branches are of a parallel circuit that have equal resistances, the currents through all of the branches will also be equal. So again, this only means that if we have the same resistance or resistors in our parallel resistors, power is just the sum of all the individual powers of the resistors. So the formula for power that we used before will still be applicable to the parallel circuit. Now, if one branch is open or broken, it's open, the total resistance will increase and the total current will decrease. If a branch opens, there is still current, but it will not go to that branch, but it will go to the other resistors. So there you go. This is the summary, and I hope you learned all the necessary things about the parallel circuits. Because in the next videos, I will be showing you how to calculate or do more calculations on parallel circuits. So thank you so much, and I hope you watch these videos again and again until you understand the lesson or the topics that were discussed today. So thank you so much. Please like, subscribe, and share these videos. And thank you. This is from ERC Tips Knowledge. Have a nice day.